Hi everyone. So in this video we'll introduce a simple example. Now we know the basics of backpropagation, how it works. To make this understanding concrete, let's give an example in a fully connected multi-layer perceptron using just one input example. Right? So please note that in a practical application, we usually use a mini batch of training examples, and that's what we will do in the next video. We will extend that example to basically, instead of having one input example, you have a list of examples, right? So let's call that example, we set it in a variable called h0, and there is a reason for this notation, is that h will always be the output of the hi will be the output of the ith layer. So this is the 0th layer, which is the input layer. And then for k equal 1 to L, where L is the depth of the network, so this is the forward propagation, right? First, we compute the outputs A of k of the kth layer pre the nonlinear activations, right? So this consists of the biases B of k plus the weight times h of k minus 1, right? So in the first layer, this is h of 0 is the input times the weights, right? Plus the biases to get the pre-nonlinear activation. Now note that x, h of 0, a of k, and b of k, these could all be vectors, and w of k could be a matrix, right? So w defines a matrix that determines the weights between the two vectors a and a of k, or a of 1 in the first layer, and h of 0, a of k and h of k minus 1, right? So we compute the pre-nonlinear activations, and then we apply the nonlinear activations. Let's say it's a function f, so h of k is f a of k. Then this computes all the intermediate computations of the neural network. Then we have the prediction y hat. Let's say this is a classification problem. Even if it's a regression, there is a prediction of the function. This is h of L, where L is the depth of the function. So this is the output of the last layer. Then we apply the cost function, we call it j, and this corresponds of a loss between y hat, which is the prediction of the neural network, and the label given with that training example, plus lambda, which is a regularization coefficient, times a regularizer gamma of theta. Now theta is the vector of parameters. As we said before, it includes all the weights and biases. Then we apply a regularization function times a regularization coefficient. Now now as we are concluding the first section of this course, the second section, the coming section, will be on regularization. So we'll understand why it's not just the loss function, why we add this regularizer, and when do we need it. And it's mainly used for generalization, to extract concepts that generalize beyond the exact details of the training data that we have seen. So this is the forward propagation, and now that we have established the notation, let's see how to backpropagate that simple example. So after backpropagation, we compute the gradient with respect to the output of the last layer, which is the prediction, y hat, right? So we compute the gradient of the loss j with respect to y hat. And this is basically the gradient with respect to y hat of the loss function L, y hat and y, right? So that basically computes for a very small change in y hat, how will the loss function will change. And that will give us an idea on how the prediction should change in a direction that minimizes the loss. And then we go backward, right? So here the for loop goes from L to 1, right? So from the last layer to the first layer. We have G is the value of the current gradient with respect to the output of the current layer. Then we update this G. How do we update it? So first, we compute the gradient with respect to the pre-nonlinearity, right? So this gradient G here is with respect to the output of the layer, right? So remember, we call y hat h of L, the output of the Lth layer. in general, as we go through the for loop, G will have the value of the gradient of the output with respect to the output of the layer. Now we go one step backward. So the output of the layer after nonlinear, we go to the pre-nonlinearity. So this is the gradient of J with respect to A of K, the output of pre-nonlinearity. And this is basically G times element-wise multiplication. Now remember, G will also be a vector because H is a vector and A is a vector. So you have a vector of gradients, right? The width of the vector corresponding to the number of units in that layer. And then you apply element-wise multiplication with F prime. F is the nonlinear activation function of A of K. So F prime, for example, if you have a ReLU, right? The active ReLUs will have a gradient of 1. The non-active ReLUs will have a gradient of 0, right? Because a ReLU is 0 and then it becomes a line, right? So the non-active ones is 0, the active ones is 1. So if that's a ReLU, what this step is doing is basically it's filtering the gradients, zeroing out the gradients corresponding to the non-active ReLUs, right? If it's another general activation function that comes with its own derivative, right? And we said in TensorFlow, for example, it comes with its own definition of how to backpropagate that function. Then we need that here. So G times the derivative of the activation function at the current values, right? So now in this step, note that this is why we need to compute forward propagation first before constructing the backpropagation computational graph, right? Because I need to compute the activations so that I know the value of F prime of A of K. I need to know the value of A of K first, right? So then we backpropagate. This is G, this is the gradient with respect to the output pre-nonlinearity. And then we compute the gradient with respect to the biases. So remember, this A of K consists of B of K plus W of K times H of K minus 1, right? So the gradient with respect to B of K is basically the same, G, right? Because it will be multiplied by the derivative of A of K with respect to B of K, which is unity, right? Because B of K is not multiplied by anything. And plus lambda times the gradient of the regularizer. So remember, it's not just the loss function. So here, there is no gradient of the regularizer with respect to the prediction because the regularizer doesn't depend on the prediction. The regularizer depends on the parameters, right? So in this step, we have the gradient of the regularizer with respect to B of K, the biases. Now this is typically 0. And the reason we will shed more light on the reason behind this when we come to the regularization section. But regularizers usually are functions only of the weight parameters, not the biases. And then we compute the gradient with respect to the weights, W of K. So what's the relationship between A of K and W of K? A of K equals W of K times H of K minus 1 plus the B of K, right? So the gradient G here is the gradient with respect to A of K, right, from this step. Then I multiply it by H of K minus 1 transpose, right? So the first derivative, if A equal H times W, then dA by dW is just H. And that's what we are doing here, right? Plus lambda, the gradient of the regularizer with respect to W of K. Now this is typically has a value, non-zero, because the regularizer is a function of the weight parameters. So now we computed the gradient successfully with respect to the parameters of that layer, and that's the objective, the B of K and the W of K. And then we want to propagate the gradient to the layer before. So then we update J with the value of the gradient of J with respect to H of K minus 1, and that will be equal W of K transpose times G, right? Because G here is the gradient with respect to the A of K pre-nonlinearity, and this A of K, the relationship to W is that it's equal to, the relationship with H is that it's equal to H times W. So the gradient with respect to H will be equal to the gradient, to W times the gradient with respect to A. Right? So then we propagate to the last layer and then we go on with the for loop. Right? So every step, you see here that you have typically a vector-to-vector multiplication, the G with the H. Here you have a matrix and vector multiplication, plus computing the value of the gradient with respect to the regularizer. The regularizer is usually a direct function of the weight parameters, so there is no need to backpropagate in the computation of the regularizer gradient, right? You directly compute it with respect to the weights in every step of backpropagation. Thank you.